26 light-years from Earth, floating in the cosmic darkness around a red dwarf star, exists a world that has fundamentally changed our understanding of life in the universe. This planet, designated K218b, has become the first confirmed exoplanet where the James Webb Space Telescope has detected the unmistakable signature of oxygen in its atmosphere. The discovery represents more than just another scientific milestone. It marks the beginning of a new era in astronomy, one where we can peer into the atmospheric composition of distant worlds with unprecedented precision and ask the profound question that has haunted humanity for millennia: are we alone? The James Webb Space Telescope, humanity's most powerful eye on the cosmos, achieved what was once considered impossible through its revolutionary infrared capabilities. It analyzed light that had traveled for 26 years across the void, light that had passed through the atmosphere of an alien world and carried with it the chemical fingerprints of that distant realm. Among those fingerprints, nestled within the spectral data like a cosmic signature, was the clear indication of molecular oxygen, the same gas that fills our lungs and sustains life on Earth. The implications of this discovery ripple far beyond the confines of astronomical journals and research institutions. Oxygen, as we understand it, is not merely another atmospheric component. On Earth, virtually all the oxygen in our atmosphere exists because of life. Plants, algae, and cyanobacteria have been pumping oxygen into our atmosphere for billions of years through the process of photosynthesis. Without life, Earth's oxygen would have long since been consumed by chemical reactions with rocks and metals. The presence of oxygen on K218b suggests that similar processes might be occurring on that distant world. K218b orbits within what astronomers call the habitable zone, that Goldilocks region around a star where temperatures are just right for liquid water to exist. On a planet's surface, the planet is roughly 2.6 times the radius of Earth and about 8.6 times more massive, placing it in a category of worlds that our solar system lacks entirely. These super-Earths, as they're known, are among the most common types of planets in our galaxy, yet until recently, they remain mysterious and largely unexplored. The red dwarf star that K218b orbits burns cooler and dimmer than our Sun, but it also burns longer. These stellar remnants can shine for trillions of years, providing stable energy sources for potentially habitable worlds. Red dwarfs make up about 75% of all stars in our galaxy, making them prime candidates for harboring life-bearing planets. The fact that we've now detected oxygen around one of these systems opens up the possibility that life might be far more common than we ever imagined. The journey to this discovery began years before the James Webb Space Telescope ever captured its first image. K218b was originally identified by NASA's Kepler Space Telescope through the transit method, where astronomers detect the tiny dimming of starlight as a planet passes in front of its host star. Follow-up observations by the Hubble Space Telescope revealed the presence of water vapor in the planet's atmosphere, making it a prime target for more detailed analysis by Webb. When the James Webb Space Telescope turned its instruments toward K218b, it employed a technique called transmission spectroscopy. As the planet transited its star, starlight filtered through the planet's atmosphere, and different molecules absorbed specific wavelengths of that light. By analyzing which wavelengths were absorbed, scientists could determine the chemical composition of the atmosphere with remarkable precision. The data revealed a complex atmospheric chemistry. Along with oxygen, Webb detected water vapor, carbon dioxide, and possibly dimethyl sulfide, a molecule that on Earth is only produced by living organisms. The combination of these gases paints a picture of a world that might be fundamentally different from anything in our solar system, yet eerily familiar in its potential to harbor life. The discovery challenges our preconceptions about where life might exist in the universe. For decades, astronomers focused primarily on Earth-sized planets orbiting sun-like stars. K218b suggests that we need to expand our search parameters dramatically. Super-Earths orbiting red dwarf stars might represent the most common type of potentially habitable world in our galaxy. The technical achievement represented by this discovery cannot be overstated. The James Webb Space Telescope detected these atmospheric components across a distance of 26 light-years. analyzing an atmosphere that is thousands of times thinner than what we can observe directly. The precision required is analogous to detecting the chemical composition of a candle flame from thousands of miles away while that flame is backdropped by a blazing bonfire. This breakthrough opens the door to a systematic survey of potentially habitable exoplanets. With thousands of known exoplanets and new discoveries being made regularly, astronomers now have the tools to search for atmospheric signatures of life across a broad range of worlds. The oxygen detection on K2-18b provides a template for future observations and a proof of concept that such detailed atmospheric analysis is possible with current technology. The story of this discovery is also the story of human ingenuity and persistence. It represents the culmination of decades of technological development. From the initial conception of space-based infrared telescopes to the engineering marvels that made Webb possible, it showcases the power of international collaboration in science and the importance of investing in fundamental research that pushes the boundaries of human knowledge. Telescope revolution. The James Webb Space Telescope stands as humanity's most ambitious attempt to peer into the depths of space and time. Positioned 1.5 million kilometers from Earth at the second Lagrange point, Webb operates in the cold darkness of space, its instruments cooled to temperatures approaching absolute zero. This positioning and cooling are not merely technical preferences, but absolute necessities for the telescope's groundbreaking infrared observations. Webb's mirror, composed of 18 hexagonal segments of beryllium coated in gold, spans 6.5 meters in diameter, providing nearly 7 times the light-gathering power of its predecessor, the Hubble Space Telescope. The choice of beryllium was crucial for infrared astronomy. This lightweight metal maintains its shape even at the extreme cold temperatures required for infrared observations, while the gold coating ensures maximum reflectivity for infrared light. The telescopes for primary instruments work in concert to dissect the light from distant objects across the infrared spectrum. The near-infrared camera, or NIRCam, serves as Webb's primary imaging device, capable of detecting light from the very first stars and galaxies that formed after the Big Bang. The near-infrared spectrograph, NIRSpec, can simultaneously observe hundreds of objects, breaking their light into component wavelengths to reveal their chemical composition and physical properties. The mid-infrared instrument, MIRI, operates at longer infrared wavelengths and requires additional cooling beyond what the telescope's passive cooling system can provide. MIRI employs a Cryo cooler that reduces its temperature to just 7 degrees above absolute zero, enabling it to detect the thermal emission from warm objects like planets and circumstellar disks. The Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph, FGS NIRIS, provides the precise pointing control necessary for long-exposure observations while also contributing to exoplanet science. The development of Webb required solving engineering challenges that pushed the boundaries of what was considered possible. The telescope's sunshield, roughly the size of a tennis court, consists of 5 layers of specially designed material that block the heat and light from the Sun, Earth, and Moon. This sunshield maintains a temperature difference of more than 300 degrees Celsius between its sun-facing and space-facing sides, creating the cold environment necessary for infrared observations. The deployment of Webb represented one of the most complex engineering sequences ever attempted in space, following its launch on Christmas Day 2021. The telescope underwent a months-long deployment process that required hundreds of precise mechanical operations. Each step in this sequence had to work perfectly, as Webb's position at the second Lagrange point placed it far beyond the reach of any servicing mission. Webb's infrared capabilities opened new windows into the universe that were previously invisible to ground-based telescopes and even to Hubble. Earth's atmosphere blocks most infrared radiation, making space-based infrared astronomy essential for studying cool objects like planets, brown dwarfs, and the earliest galaxies in the universe. Webb's sensitivity allows it to detect infrared radiation from objects billions of times fainter than what the human eye can see. The telescope's impact on exoplanet science has been revolutionary. Previous methods of studying exoplanet atmospheres were limited to the largest and hottest worlds, typically gas giants orbiting very close to their stars. Webb's sensitivity extends atmospheric studies to smaller, cooler planets that might be more conducive to life as we know it. The telescope can detect atmospheric components at concentrations measured in parts per million, revealing the detailed chemistry of alien worlds. Webb's approach to exoplanet atmospheric analysis relies primarily on transmission spectroscopy and emission spectroscopy. In transmission spectroscopy, astronomers observe a star as an exoplanet passes in front of it, analyzing how the planet's atmosphere filters the starlight. Different molecules absorb specific wavelengths of light, creating absorption lines in the spectrum that serve as fingerprints for those molecules. Emission spectroscopy involves measuring the thermal radiation from the planet itself, typically when the planet is at its hottest point in its orbit, by comparing observations taken when the planet is visible to those taken when it's hidden behind its star. Astronomers can isolate the planet's thermal emission and study its atmospheric composition and temperature structure. The precision required for these observations demands extraordinary stability and accuracy. Webb must maintain its pointing to within a few milliseconds over periods of many hours. To put this in perspective, this level of precision is equivalent to holding a laser pointer steady enough to hit a coin from a distance of 100 kilometers. The telescope's fine guidance system uses guide stars to maintain this remarkable stability. Webb's discovery of oxygen on K2218b represents the culmination of technological developments that began decades before the telescope's launch. The infrared detectors used in Webb's instruments are marvels of engineering, capable of detecting individual photons of infrared light. These detectors are made from exotic materials like mercury cadmium telluride and operate at temperatures so cold that thermal motion of atoms is virtually eliminated. The data processing required for Webb's observations involves sophisticated algorithms and computational techniques. The raw data from the telescope undergoes multiple stages of processing to remove instrumental effects and noise, revealing the underlying astronomical signals. For exoplanet observations, this processing must account for the tiny variations in stellar brightness caused by the planet's atmosphere, signals that are often thousands of times smaller than the noise level in the raw data. Webb's success builds upon decades of infrared astronomy from space. Earlier missions like the Infrared Astronomical Satellite, the Spitzer Space Telescope, and the Herschel Space Observatory laid the groundwork for Webb's achievements. Each of these missions advanced our understanding of infrared astronomy and contributed to the technological development that made Webb possible. The international collaboration that made Webb possible involved thousands of scientists, engineers, and technicians from NASA, the European Space Agency, and the Canadian Space Agency. This collaboration ensured that Webb incorporated the best ideas and technologies from around the world, creating a telescope that no single nation could have built alone. Webb's impact extends beyond its individual discoveries to its role in training a new generation of astronomers and engineers. The telescope's complex operations and data analysis techniques are pushing the boundaries of what's possible in astronomical observation, creating new methodologies that will benefit future missions and ground-based observatories. The telescope's versatility allows it to address fundamental questions across multiple areas of astronomy. While its exoplanet observations capture public attention, Webb is simultaneously studying the formation of the first galaxies, birth of stars in nearby molecular clouds, and the evolution of our own solar system. This breadth of capability makes Webb a transformative tool for all of astronomy. K218b, the target K218b, occupies a unique position in the catalog of known exoplanets, representing a type of world that exists nowhere in our solar system yet appears to be among the most common planetary types in our galaxy, located 26 light-years away in the constellation Leo. This super-Earth orbits a red dwarf star designated K218, offering astronomers a nearby laboratory for studying potentially habitable worlds fundamentally different from our own. The planet was first identified in 2015 by NASA's Kepler Space Telescope during its K2 mission, an extended phase of operations following the failure of two of Kepler's reaction wheels. The K2 mission, despite its technical limitations, proved remarkably successful at discovering exoplanets around nearby stars. K218b was detected through the transit method, where astronomers measure the periodic dimming of starlight as the planet passes in front of its host star. K218b completes an orbit around its star every 33 Earth days, placing it squarely within the habitable zone where liquid water could potentially exist on the planet's surface. The habitable zone, sometimes called the Goldilocks zone, represents the range of distances from a star where a planet receives enough energy to maintain liquid water but not so much that the water boils away into space. The planet's physical characteristics place it in the super-Earth category, with a radius approximately 2.6 times that of Earth and a mass roughly 8.6 times greater. This size and mass combination gives K218b a density suggesting it likely has a substantial atmosphere and possibly significant amounts of water. The planet's composition probably includes a rocky core surrounded by a deep atmosphere and potentially a global ocean beneath that atmosphere. The red dwarf star K218 presents a very different environment compared to our Sun. Red dwarfs are much smaller, cooler, and dimmer than Sun-like stars, but they have extraordinary lifespans that can extend for trillions of years. K2-18 has a mass about 1/3 that of our Sun and a temperature of approximately 3,400 Kelvin, compared to the Sun's 5,778 Kelvin, despite being cooler. The star's longevity means that planets in its habitable zone could potentially maintain stable conditions for life over vastly longer periods than planets around Sun-like stars. The close orbital distance required for a planet to be habitable around a red dwarf creates unique conditions that don't exist in our solar system. K218b orbits its star at a distance of only 0.1 for astronomical units, roughly 1/7 the distance between Earth and the Sun. At this distance, the planet likely experiences tidal locking, meaning one side always faces the star while the other side remains in permanent darkness. Tidal locking creates extreme temperature gradients between the day and night sides of the planet, but atmospheric circulation could potentially redistribute heat around the globe. Computer models suggest that planets with substantial atmospheres can maintain relatively stable temperatures even under tidally locked conditions. The thick atmosphere inferred for K218b might enable such heat redistribution, creating a more temperate environment than the extreme day-night temperature differences would suggest. The planet's size places it in a category that planetary scientists are still working to understand. Super-Earths represent a missing link between terrestrial planets like Earth and ice giants like Neptune. Some super-Earths might be scaled-up versions of rocky planets, while others could be mini-Neptunes with thick hydrogen-helium atmospheres. Determining which type K218b represents is crucial for understanding its potential habitability. Recent modeling suggests that K218b might be what scientists call a Hycean world, a new class of potentially habitable exoplanets characterized by hydrogen-rich atmospheres and global oceans. Hycean worlds could be habitable under a much broader range of conditions than traditional rocky planets, potentially expanding the number of worlds that could support life by orders of magnitude. The discovery process for K218b illustrates the collaborative nature of modern exoplanet science. Following Kepler's initial detection, ground-based telescopes conducted follow-up observations to confirm the planet's existence and refine measurements of its orbital period and size. The Hubble Space Telescope later detected water vapor in the planet's atmosphere, making it a prime target for more detailed study by the James Webb Space Telescope. K218b's proximity to Earth, in astronomical terms, makes it an ideal target for atmospheric studies. At 26 light-years away, the planet is close enough that its host star appears relatively bright, providing sufficient photons for detailed spectroscopic analysis. The planet's size and orbital period also create favorable conditions for transit observations, as the planet blocks a measurable fraction of its star's light during each transit. The planet's atmospheric composition, as revealed by Webb's observations, suggests a complex chemistry that could potentially support life. The presence of water vapor, carbon dioxide, and oxygen creates conditions that are at least reminiscent of Earth's atmosphere. Though the overall composition is likely very different, the possible detection of dimethyl sulfide, a molecule that on Earth is only produced by living organisms, adds another tantalizing piece to the habitability puzzle. Understanding K218b requires placing it in the context of other super-Earths discovered around red dwarf stars. The TRAPPIST-1 system, located 40 light-years away, contains 7 Earth-sized planets orbiting an ultra-cool red dwarf. Several of these planets orbit within the habitable zone, though they appear to lack the substantial atmospheres that K218b possesses. The diversity among these systems highlights the range of potentially habitable environments that might exist around red dwarf stars. The magnetic field properties of K218b represent another important factor in its potential habitability. Red dwarf stars are known for producing powerful stellar flares and high levels of ultraviolet and X-ray radiation that could strip away planetary atmospheres. A strong planetary magnetic field could provide protection against this radiation. But determining whether K218b possesses such a field remains beyond current observational capabilities. The atmospheric pressure on K218b is likely much higher than on Earth, possibly reaching levels similar to those found on Venus or even higher. High atmospheric pressure could enable liquid water to exist at temperatures above 100 degrees Celsius, expanding the range of potentially habitable conditions. However, extremely high pressures could also create challenges for life as we know it. The science of atmospheric detection. The detection of atmospheric components on distant exoplanets represents one of the most technically challenging achievements in modern astronomy. The process requires extracting incredibly subtle signals from overwhelming background noise, analyzing light that has traveled across vast cosmic distances while carrying within its spectral signature the chemical fingerprints of alien worlds. Transmission spectroscopy, the primary technique used to study K218b's atmosphere, exploits the fact that when a planet passes in front of its star, some of the starlight filters through the planet's atmosphere before reaching Earth. Different molecules in the atmosphere absorb specific wavelengths of light, creating absorption lines in the spectrum that serve as unique identifiers for those molecules. The physics underlying this process relies on the quantum mechanical properties of atoms and molecules. When a photon of light encounters a molecule, it can be absorbed if the photon's energy exactly matches the energy difference between two quantum states of that molecule. Oxygen molecules, for example, absorb specific wavelengths of infrared light corresponding to transitions between their rotational and vibrational energy states. The challenge lies in the extraordinary precision required to detect these absorption signatures. The atmosphere of K218b intercepts only a tiny fraction of the total starlight, and the absorption by atmospheric molecules creates variations in brightness that are typically measured in parts per million. Detecting such minute changes requires instruments with exceptional sensitivity and stability. The James Webb Space Telescope's infrared capabilities prove crucial for this type of analysis because many important atmospheric molecules have their strongest absorption features in the infrared portion of the electromagnetic spectrum. Water vapor, carbon dioxide, methane, and molecular oxygen all exhibit prominent infrared absorption lines that are virtually impossible to observe from ground-based telescopes due to absorption by air. Zone atmosphere. Webb's approach to atmospheric analysis involves multiple observations taken at different points in the planet's orbit. When the planet is transiting its star, astronomers measure the combined light from the star and the filtered light that has passed through the planet's atmosphere. They compare this to observations taken when the planet is not transiting, allowing them to isolate the spectral signature of the atmosphere itself. The data reduction process for these observations involves sophisticated statistical analysis and computer modeling, where observations contain noise from multiple sources, thermal fluctuations in the detector, cosmic ray impacts, stellar variability, and systematic effects from the telescope and instruments. Separating the planetary atmosphere signal from this noise requires careful calibration and advanced data processing techniques. Stellar activity presents one of the most significant challenges in atmospheric detection. Red dwarf stars like K218 are known for their variable behavior, including stellar flares and spots that can create brightness changes much larger than the atmospheric signals astronomers seek to measure. Distinguishing between stellar variability and genuine atmospheric absorption requires long-term monitoring and careful analysis of the star's behavior. The interpretation of atmospheric spectra involves comparing observed data with theoretical models of planetary atmospheres. These models account for the temperature and pressure structure of the atmosphere, the abundance of different chemical species, and the complex interactions between molecules and radiation. Creating accurate models requires understanding atmospheric chemistry, radiative transfer, and the dynamics of atmospheric circulation. Molecular oxygen detection presents particular challenges because oxygen can exist in planetary atmospheres through both biological and non-biological processes. On Earth, photosynthesis by plants and microorganisms produces virtually all atmospheric oxygen. However, oxygen can also result from the photodissociation of water vapor by ultraviolet radiation, followed by the escape of hydrogen to space. Distinguishing between these processes requires additional information about the planet's atmosphere and environment. The detection threshold for different molecules varies significantly based on their absorption properties and the observational conditions. Water vapor and carbon dioxide are relatively easy to detect because they have strong absorption features in wavelength regions where Webb is most sensitive. Oxygen detection is more challenging because molecular oxygen's primary absorption features occur in wavelength regions where the telescope's sensitivity is lower. Contamination from Earth's atmosphere poses an additional challenge for infrared observations. Even for space-based telescopes, although Webb operates outside Earth's atmosphere, scattered light from Earth can still affect observations, particularly for molecules that are abundant in our own atmosphere. Careful observational planning and data analysis techniques are required to minimize these effects. The statistical significance of atmospheric detections requires rigorous analysis to distinguish genuine signals from random noise fluctuations. Astronomers typically require detection confidence levels of 3 to 5 sigma, meaning the probability that the observed signal results from random noise is less than 1 in 1,000 to 1 in 3.5 million, respectively. Achieving these confidence levels for weak atmospheric signals often requires combining data from multiple observations. Cross-contamination between different molecular species represents another source of uncertainty. In atmospheric analysis, the absorption features of different molecules can overlap in wavelength, making it difficult to determine the exact abundance of each species. Advanced modeling techniques and observations at multiple wavelengths help resolve these ambiguities, but uncertainties remain. The temporal stability of atmospheric signatures provides important information about the planet's atmospheric dynamics and chemistry. Observations taken at different times can reveal changes in atmospheric composition due to weather patterns, seasonal variations, or long-term chemical evolution. For K2-18b, multiple observations will help confirm the persistence of the detected oxygen signal. Temperature and pressure conditions in the planet's atmosphere affect the strength and shape of molecular absorption features. Molecules at higher temperatures have broader absorption lines due to increased thermal motion, while pressure broadening occurs when molecules collide frequently at high atmospheric densities. Modeling these effects requires detailed understanding of the atmospheric structure. The altitude at which different molecules exist in the atmosphere influences their detectability. Molecules concentrated in the upper atmosphere are more easily detected because they interact with more of the incoming starlight. Understanding the vertical distribution of atmospheric components requires complex atmospheric models that account for chemical reactions, atmospheric mixing, and thermal structure. Future improvements in atmospheric detection capabilities will come from both technological advances and improved analysis techniques, next-generation telescopes with larger mirrors, and more. Sensitive detectors will enable the study of smaller planets and weaker atmospheric signals. Advanced computer models and machine learning techniques will help extract more information from existing observations. The study of K2-18b's atmosphere represents just the beginning of a systematic survey of exoplanet atmospheres. With thousands of known exoplanets and new discoveries being made regularly, astronomers are developing the observational and analytical tools needed to characterize the atmospheric properties of potent highly habitable worlds throughout our galactic neighborhood. Oxygen in planetary atmospheres. Oxygen occupies a unique position in the search for extraterrestrial life, serving as both one of the most promising biosignatures and one of the most controversial indicators of biological activity. The detection of molecular oxygen in K218b's atmosphere raises profound questions about the interpretation of atmospheric composition and the processes that can produce this reactive gas. On alien worlds. On Earth, molecular oxygen comprises approximately 21% of our atmosphere, a concentration that has been maintained for hundreds of millions of years through the continuous activity of photosynthetic organisms. This oxygen abundance represents a dramatic departure from the reducing atmosphere that characterized early Earth, when oxygen levels were virtually zero and the atmosphere consisted primarily of methane, ammonia, and other reduced compounds. The transformation of Earth's atmosphere began approximately 2.4 billion years ago during what geologists call the Great Oxidation Event. Cyanobacteria, among the first organisms capable of oxygenic photosynthesis, began producing oxygen as a byproduct of their metabolism. Initially, this oxygen was consumed by chemical reactions with iron and other reduced compounds in the oceans and rocks. Only when these oxygen sinks became saturated did free oxygen begin to accumulate in the atmosphere. The presence of free oxygen in Earth's atmosphere represents a fundamental disequilibrium that requires constant biological maintenance. Oxygen is highly reactive and would quickly disappear from the atmosphere if not continuously replenished. Geological processes consume atmospheric oxygen through oxidation reactions with volcanic gases, mineral weathering, and organic matter burial. Without the constant production of oxygen by photosynthesis, Earth's atmospheric oxygen would be depleted within a few million years. This understanding has led astrobiologists to consider oxygen as a potential biosignature, a gas whose presence in an exoplanet's atmosphere might indicate biological activity. The reasoning is straightforward: if oxygen cannot persist in planetary atmospheres without continuous replenishment, and if biological processes represent the most efficient known mechanism for oxygen production, then detecting oxygen on an exoplanet might suggest the presence of life. However, the interpretation of oxygen as a biosignature proves far more complex than this simple reasoning suggests. Multiple non-biological processes can produce oxygen in planetary atmospheres, and distinguishing between biological and non-biological oxygen sources requires careful analysis of the planet's overall atmospheric composition and environmental conditions. Photodissociation represents the most significant non-biological mechanism for oxygen production in planetary atmospheres. High-energy ultraviolet radiation from a planet's host star can break apart water vapor molecules in the upper atmosphere, producing hydrogen and oxygen atoms. The lighter hydrogen atoms can escape to space, while oxygen atoms can combine to form molecular oxygen. This process is particularly efficient on active red dwarf stars that produce high levels of ultraviolet radiation. The efficiency of photodissociation depends on several factors, including the intensity of ultraviolet radiation from the host star, the amount of water vapor in the planet's atmosphere, and the planet's ability to retain hydrogen. Planets with strong magnetic fields are better able to retain hydrogen, reducing the efficiency of oxygen production through water photodissociation. Conversely, planets lacking magnetic protection might lose hydrogen rapidly, leading to significant oxygen accumulation. Atmospheric escape processes play a crucial role in determining whether photodissociated oxygen accumulates in the atmosphere or is lost to space. Light planets with weak gravitational fields might lose both hydrogen and oxygen to space, preventing the buildup of either gas. Massive planets with strong gravitational fields are more likely to retain both gases, but they might also retain so much hydrogen that oxygen never becomes a significant atmospheric component. The vertical distribution of oxygen in the atmosphere provides important clues about its origin. Biologically produced oxygen typically becomes well mixed throughout the atmosphere due to atmospheric circulation and the continuous production of oxygen at the planet's surface. Photodissociated oxygen, by contrast, is initially produced in the upper atmosphere and might remain concentrated at high altitudes, particularly if atmospheric mixing is limited. Oxygen chemistry in planetary atmospheres involves complex networks of chemical reactions that can both produce and destroy oxygen molecules. Reactions with hydrogen, methane, and other reduced compounds can consume oxygen, while reactions with ozone can both produce and destroy oxygen through catalytic cycles. Understanding these chemical networks requires detailed atmospheric models that account for temperature, pressure, and the abundances of multiple chemical species. The presence of other gases in the atmosphere can provide crucial context for interpreting oxygen detections. Water vapor indicates the potential for photodissociation chemistry, while the presence of reduced gases like methane or hydrogen sulfide might suggest active geological or biological processes that could interact with atmospheric oxygen. The overall oxidation state of the atmosphere helps determine whether oxygen can accumulate or will be quickly consumed by chemical reactions. Temporal variations in oxygen abundance could potentially distinguish between biological and non-biological sources. Biological oxygen production might show seasonal variations related to planetary climate cycles or long-term changes related to ecosystem evolution. Non-biological oxygen production through photodissociation might be more steady over time, though it could vary with stellar activity cycles or changes in atmospheric water vapor content. The detection of oxygen in combination with other potential biosignatures strengthens the case for biological activity. The simultaneous presence of oxygen and methane, for example, represents a particularly strong disequilibrium signature because these gases react rapidly with each other under most atmospheric conditions. Maintaining both gases in the same atmosphere requires continuous replenishment, potentially from biological sources. Dimethyl sulfide, possibly detected in K218b's atmosphere, represents another potential biosignature that could support biological interpretation of the oxygen detection. On Earth, dimethyl sulfide is produced exclusively by living organisms, primarily marine phytoplankton. The combination of oxygen and dimethyl sulfide might provide stronger evidence for biological activity than either gas alone. The interpretation of oxygen detections must also consider the age and evolutionary history of the planetary system. Young planets might retain primordial atmospheres rich in hydrogen and other reduced compounds. That would prevent oxygen accumulation. Older planets have had more time for atmospheric evolution and the development of complex chemical cycles that could either produce or consume oxygen. Red dwarf stellar environments present unique challenges for oxygen interpretation. These stars are known for producing intense stellar flares that deliver high-energy radiation to planetary atmospheres. Such radiation could drive efficient photodissociation of water vapor, potentially producing significant amounts of oxygen through non-biological processes. However, the same radiation might also strip away planetary atmospheres entirely, creating a complex interplay between oxygen production and atmospheric loss. Comparative studies of multiple planets around the same star could help resolve ambiguities in oxygen interpretation. If oxygen is detected on multiple planets in a system, non-biological processes related to stellar radiation might be more likely than independent biological evolution on multiple worlds. Conversely, oxygen detection on only one planet in a multi-planet system might support a biological interpretation. The abundance of oxygen relative to other atmospheric components provides additional constraints on its origin. Biological oxygen production typically maintains oxygen at levels that depend on the balance between production and consumption rates. Photodissociation could potentially produce oxygen abundances that are either much higher or much lower than biologically maintained levels. Depending on the specific environmental conditions, laboratory studies of oxygen chemistry under various atmospheric conditions help inform the interpretation of exoplanet observations. These studies explore the reaction rates and pathways that control oxygen abundance under different temperature, pressure, and compositional conditions. Such research provides the fundamental data needed to construct accurate atmospheric models and interpret observational results. The detection process, the journey from raw photons detected by the James Webb Space Telescope to the definitive identification of oxygen in K218b's atmosphere. represents one of the most sophisticated data analysis challenges in modern astronomy. This process involves multiple stages of data reduction, calibration, and interpretation, each requiring careful attention to potential sources of error and systematic effects. The observational campaign for K2-18b began months before the actual data collection, with detailed planning to optimize the telescope's configuration for atmospheric detection. Astronomers calculated the precise timing of the planet's transits, determined the optimal exposure times and observing strategies, and configured the telescope's instruments to maximize sensitivity to the wavelength regions where atmospheric absorption features were expected to appear. Webb's observations of K2-18b employed the near-infrared spectrograph, NIRSPEC, operating in its bright object mode to handle the relatively bright light from the host star. The instrument was configured to observe simultaneously across multiple wavelength ranges, from approximately 1 to 5 micrometers, covering the spectral regions where water vapor, carbon dioxide, and molecular oxygen produce their strongest absorption features. The actual observations consisted of a carefully orchestrated sequence of measurements taken before, during, and after the planet's transit. Pre-transit observations established the baseline stellar spectrum and monitored for any stellar variability that might affect the atmospheric measurements. Transit observations captured the combined light from the star and the filtered light that passed through the planet's atmosphere. Post-transit observations provided additional baseline measurements and helped assess the stability of the stellar output. Each individual observation consisted of multiple exposures designed to build up sufficient signal while avoiding detector saturation. The exposures were carefully timed to sample different phases of the planet's transit, allowing astronomers to track how the stellar spectrum changed as different portions of the planet's atmosphere set in front of the star. This temporal sampling proved crucial for distinguishing genuine atmospheric absorption from systematic instrumental effects. The raw data from Webb's detectors underwent extensive calibration to remove instrumental signatures and convert the measurements into calibrated spectra. This process included corrections for detector nonlinearity, flat field variations across the detector surface, wavelength calibration, and flux calibration. Each step required careful validation using calibration observations of standard stars and other reference sources. Cosmic ray impacts presented a significant challenge during the long exposures required for atmospheric detection. High-energy cosmic ray particles striking the detector create bright spots that can contaminate the spectroscopic measurements. Sophisticated algorithms identified and removed these cosmic ray events while preserving the underlying astronomical signals. The extraction of one-dimensional spectra from the two-dimensional detector images required careful modeling of the instrument's point spread function and precise tracking of how the stellar spectrum was distributed across the detector. Small shifts in the telescope's pointing or changes in the instrument's thermal environment could affect this distribution, requiring real-time monitoring and correction. Stellar variability correction represented one of the most critical aspects of the data analysis. Red dwarf stars like K2-18 are known for their variable behavior, including brightness fluctuations due to stellar spots, flares, and other magnetic activity. These variations can create spectral changes that mimic atmospheric absorption features, making it essential to distinguish between stellar and planetary effects. The analysis team employed multiple techniques to address stellar variability. They monitored the star's brightness outside of transit to characterize its natural variability patterns. They also analyzed the wavelength dependence of any observed variations, using the fact that stellar effects typically have different wavelength signatures than atmospheric absorption features. The planet's atmospheric signal was isolated by comparing the in-transit and out-of-transit observations. This process, known as transit light curve analysis, involved careful modeling of how the planet's atmosphere absorbed different wavelengths of light as it passed in front of the star. The resulting transmission spectrum revealed the wavelength-dependent absorption signature of the planet's atmosphere. Statistical analysis played a crucial role in determining the significance of the atmospheric detections. The team employed Bayesian statistical methods to quantify the probability that the observed spectral features resulted from genuine atmospheric absorption rather than random noise fluctuations or systematic effects. These methods allowed them to assign confidence levels to each molecular detection. The identification of specific molecules required comparing the observed transmission spectrum with theoretical models of atmospheric absorption. These models accounted for the quantum mechanical properties of different molecules, the temperature and pressure conditions in the planet's atmosphere, and the complex interactions between molecules and radiation. Oxygen detection proved particularly challenging because molecular oxygen's primary absorption features occur in wavelength regions where Webb's sensitivity is somewhat reduced. The analysis team had to carefully account for potential contamination from other atmospheric components and systematic instrumental effects that might mimic the oxygen absorption signature. The possible detection of dimethyl sulfide required even more careful analysis because this molecule produces relatively weak absorption features that could easily be confused with noise or systematic effects. The team employed multiple independent analysis techniques to verify this detection and assess its statistical significance. Cross-validation using different analysis methods provided additional confidence in the results. Independent teams analyzed the same data using different algorithms and modeling approaches, comparing their results to identify any systematic biases or analysis-dependent effects. Agreement between different analysis methods strengthened confidence in the reported detections. The atmospheric modeling required to interpret the observations involved sophisticated radiative transfer calculations that traced how light interacts with the planet's atmosphere at different altitudes and wavelengths. These models accounted for molecular absorption, scattering by atmospheric particles, and the complex temperature and pressure structure of the atmosphere. Uncertainty quantification represented a critical aspect of the analysis, as the atmospheric signals were often comparable in magnitude to various sources of noise and systematic error. The team employed Monte Carlo techniques to propagate uncertainties through the analysis pipeline and determine the range of atmospheric compositions consistent with the observations. The validation of the analysis pipeline involved extensive testing with simulated data sets that included realistic noise characteristics and systematic effects. These tests helped identify potential biases in the analysis methods and optimize the algorithms for detecting weak atmospheric signals in the presence of various contaminating effects. Independent confirmation of the results required careful documentation of the analysis procedures and public release of the reduced data products. This transparency allowed other research groups to validate the findings using their own analysis techniques and help build confidence in the scientific community. About the reliability of the reported detections, the interpretation of the results required. Placing the atmospheric detections in the context of current understanding of exoplanet atmospheres and potential biosignatures. The team compared their findings with theoretical predictions for different types of planetary atmospheres and assessed the implications for the planet's potential habitability and the possibility of biological activity. Quality assessment of the observations involved detailed examination of potential systematic effects that might affect the atmospheric measurements. These included thermal variations in the telescope and instruments, mechanical flexure, and contamination from scattered light. Careful monitoring and correction of these effects proved essential for achieving the precision required for atmospheric detection. The data archive and documentation process ensured that future researchers would have access to both the raw observations and the processed data products. This archival process is crucial for enabling follow-up studies and reanalysis of the data as analysis techniques continue to improve. Comparative exoplanet atmospheres. The atmospheric composition detected on K2-18b gained significant meaning when placed in the broader context of exoplanet atmospheric studies. Over the past 2 decades, astronomers have characterized the atmospheres of hundreds of exoplanets, revealing an extraordinary diversity of atmospheric compositions, structures, and dynamics that far exceeds what we observe within our own solar system. The study of exoplanet atmospheres began with observations of hot Jupiters, massive gas giant planets orbiting extremely close to their host stars. These worlds, with atmospheric temperatures reaching thousands of degrees, provided ideal targets for early atmospheric studies because their large sizes and high temperatures made their atmospheric signals relatively easy to detect. Observations revealed atmospheres dominated by hydrogen and helium, with trace amounts of water vapor, carbon monoxide, and various metal species. Hot Jupiters taught astronomers fundamental lessons about atmospheric dynamics under extreme conditions. These planets experience intense stellar radiation that drives atmospheric circulation patterns unlike anything in our solar system. Some hot Jupiters are tidally locked to their stars, creating permanent day and night sides with temperature differences of over 1,000 degrees. Atmospheric circulation redistributes heat between these regions, but the efficiency of this process varies dramatically among different planets. The detection of water vapor in hot Jupiter atmospheres marked a milestone in exoplanet science, demonstrating that space-based telescopes could identify specific molecules in alien atmospheres. However, the extreme conditions on these planets made them poor analogs for potentially habitable worlds. As observational capabilities improved, astronomers began targeting smaller, cooler planets that might be more conducive to life as we know it. The TRAPPIST-1 system provided one of the first opportunities to study the atmospheres of potentially habitable planets. This system contained 7 Earth-sized planets orbiting an ultra-cool red dwarf star, with several planets located within the habitable zone. Initial studies with the Hubble Space Telescope suggested that most of these planets lack substantial atmospheres, possibly due to atmospheric stripping by stellar radiation. Webb's observations of TRAPPIST-1 planets have provided more detailed insights into their atmospheric properties. TRAPPIST-1b, the innermost planet, shows no evidence of an atmosphere, consistent with models predicting that planets so close to red dwarf stars would lose their atmospheres to stellar radiation. TRAPPIST-1e, located in the habitable zone, also appears to lack a substantial atmosphere, though uncertainties remain about the presence of a thin atmosphere. The atmospheric diversity observed among exoplanets reflects the wide range of formation and evolutionary processes that shape planetary systems. Planets forming in the inner regions of protoplanetary disks experience different conditions than those forming farther out. Migration processes can move planets from their formation locations to very different orbital environments, dramatically altering their atmospheric properties. Many Neptunes represent another important class of exoplanets that bridge the gap between terrestrial planets and gas giants. These planets, with radii between 1.7 and 4 times Earth's radius, are among the most common types of planets in our galaxy, yet they have no analog in our solar system. Atmospheric studies reveal that many Neptunes can have a wide range of compositions, from hydrogen-dominated atmospheres similar to gas giants to water-rich atmospheres that might support habitability. The atmospheric retention properties of different planet types depend critically on their mass, composition, and stellar environment. Low-mass planets around active stars are particularly susceptible to atmospheric loss through various escape mechanisms. High-energy radiation from the host star can heat the upper atmosphere to temperatures where gases achieve escape velocity, while stellar wind interactions can strip away atmospheric material. K2-218b's atmospheric composition distinguishes it from most previously studied exoplanets in several important ways. The simultaneous detection of water vapor, carbon dioxide, and oxygen suggests a complex atmospheric chemistry that could potentially support habitability. The possible presence of dimethyl sulfide adds another layer of complexity and potential biological significance. Comparative analysis with other super-Earths around red dwarf stars reveals the uniqueness of K2-18b's atmospheric properties. Many super-Earths appear to have hydrogen-dominated atmospheres that would likely preclude surface habitability, while others may have lost their atmospheres entirely. K2-218b's ability to retain a substantial atmosphere while maintaining potentially habitable conditions makes it particularly intriguing. The atmospheric pressure on K2-18b is likely much higher than Earth's atmospheric pressure, possibly reaching levels comparable to Venus or even higher. High atmospheric pressure can enable liquid water to exist at higher temperatures and provides better protection against space radiation, but it also creates challenges for life as we know it. Understanding how high-pressure atmospheres affect habitability remains an active area of research. Atmospheric circulation patterns on tidally locked planets like K2-18b create unique climate conditions that have no parallel on Earth. Global circulation models suggest that heat transport from the day side to the night side could maintain relatively moderate temperatures across much of the planet's surface, despite the extreme day-night temperature gradient that would exist without atmospheric circulation. Cloud formation and dynamics represent another important factor in determining the habitability of planets like K2-18b. Clouds can significantly affect the planet's energy balance by reflecting incoming stellar radiation and trapping outgoing thermal radiation. The composition and distribution of clouds depend on atmospheric temperature, pressure, and composition, creating complex feedback loops that affect planetary climate. The chemical stability of different atmospheric components under various stellar radiation environments provides crucial constraints on long-term habitability. Molecules like oxygen and dimethyl sulfide could be rapidly destroyed by stellar ultraviolet radiation if they are not continuously replenished by surface or subsurface processes. Understanding these photochemical processes helps assess whether detected atmospheric components represent steady-state conditions or transient phenomena. Seasonal variations in exoplanet atmospheres could provide additional insights into atmospheric dynamics and potential habitability. Planets with elliptical orbits or oblique rotation axes might experience seasonal cycles that affect atmospheric composition and circulation patterns. Detecting such variations requires long-term monitoring campaigns that track atmospheric changes over multiple orbital periods. The role of magnetic fields in atmospheric retention and stability represents another important factor in comparative exoplanet studies. Planets with strong magnetic fields are better protected against stellar wind interactions and radiation-driven atmospheric escape. The presence or absence of magnetic fields could explain why some planets retain substantial atmospheres while others in similar environments do not. Atmospheric chemistry models for different types of exoplanets predict a wide range of potential compositions and chemical cycles. These models help interpret observational results and guide future observations by predicting which atmospheric components might be detectable under different conditions. The models also help assess the potential for different types of atmospheric chemistry to support habitability. The search for atmospheric biosignatures requires understanding the full range of processes that can affect atmospheric composition on different types of planets. Biological processes represent just one of many factors that can influence atmospheric chemistry. Distinguishing biological from non-biological processes requires careful consideration of the planet's overall environment and the specific combination of atmospheric components that are observed. Future atmospheric studies will benefit from improved observational capabilities and expanded samples of planets with detailed atmospheric characterization. The Nancy Grace Roman Space Telescope and other future missions will enable atmospheric studies of smaller, more Earth-like planets around a broader range of stellar types. These expanded capabilities will help determine how common planets with potentially habitable atmospheres are in our galaxy. Life in the universe. The detection of oxygen in K2-18b's atmosphere reverberates far beyond the confines of this single planetary system, carrying profound implications for our understanding of life's potential prevalence throughout the universe. This discovery forces us to reconsider fundamental assumptions about habitability, expand our conception of potentially life-bearing worlds, and confront the possibility that life might be far more common than our Earth-centric perspective has traditionally suggested. The traditional approach to astrobiology has focused primarily on finding Earth-like planets orbiting Sun-like stars, reasoning that life as we know it requires conditions similar to those that fostered life's emergence and evolution on our own world. This Earth analog approach has guided the design of space missions and the interpretation of exoplanet discoveries for decades, leading to an emphasis on finding planets with sizes, masses, and orbital characteristics similar to Earth. K2-18b challenges this paradigm by demonstrating that potentially habitable conditions might exist on worlds that bear little resemblance to Earth. As a super-Earth orbiting a red dwarf star, K2-18b occupies a parameter space that our solar system lacks entirely. The planet's mass, atmospheric composition, and stellar environment create conditions that have no direct analog in our planetary neighborhood. Yet these conditions might support habitability and possibly even life. The implications extend to the sheer number of potentially habitable worlds in our galaxy. Red dwarf stars comprise approximately 75% of all stars in the Milky Way, and recent surveys suggest that most red dwarfs host planetary systems. If super-Earths in the habitable zones of red dwarf stars can maintain conditions suitable for life, the number of potentially habitable worlds in our galaxy increases by orders of magnitude compared to estimates based solely on Earth-like planets or on Sun-like stars. This expanded habitability framework requires reassessing the concept of the habitable zone itself. Traditional definitions of the habitable zone focus on the range of orbital distances where liquid water can exist on a planet's surface, assuming Earth-like atmospheric conditions and compositions. K218b suggests that planets with different atmospheric compositions might be habitable under a much broader range of conditions, potentially expanding the habitable zone significantly. The Hycean world concept, which K218b might exemplify, represents a new category of potentially habitable planets characterized by hydrogen-rich atmospheres and global oceans. These worlds could be habitable under conditions of temperature, pressure, and atmospheric composition that would be hostile to life as it exists on Earth, yet might support entirely different forms of biology adapted to these unique environments. The detection of dimethyl sulfide in K218b's atmosphere, if confirmed, would represent the first potential detection of a biosignature gas on an exoplanet, on Earth. Dimethyl sulfide is produced exclusively by living organisms, primarily marine phytoplankton and certain types of bacteria. The molecule plays important roles in marine ecosystems and atmospheric chemistry, contributing to cloud formation and climate regulation. However, interpreting dimethyl sulfide as a biosignature requires careful consideration of potential non-biological production mechanisms. While no known abiotic processes produce significant amounts of dimethyl sulfide under Earth-like conditions, the unique environment of K218b might enable chemical pathways that don't exist on our planet. Distinguishing between biological and non-biological sources requires detailed understanding of the planet's atmospheric chemistry and environmental conditions. The combination of oxygen and dimethyl sulfide in the same atmosphere presents a particularly intriguing chemical signature. These molecules react with each other under most atmospheric conditions, meaning their simultaneous presence requires continuous replenishment from some source on Earth. Biological processes readily explain the presence of both gases, but confirming a biological interpretation for K218b requires ruling out alternative explanations. The possibility of life on K218b raises fundamental questions about the nature of life itself and the range of conditions under which biology might operate. Life on Earth has adapted to an extraordinary range of environments, from the crushing depths of ocean trenches to the radiation-bathed surfaces of high-altitude mountains. Extremophiles demonstrate that life can thrive under conditions once thought impossible, suggesting that the potential habitability range might be much broader than originally conceived. Astrobiology research has identified several key requirements for life as we know it: liquid water, organic compounds, energy sources, and sufficient time for biological processes to occur. K218b appears to satisfy these requirements, with evidence for water vapor in its atmosphere, the potential for organic chemistry, energy from its host star, and a stable environment over geological timescales. The red dwarf stellar environment presents both challenges and opportunities for life. Red dwarf stars produce high levels of ultraviolet and X-ray radiation, particularly during their youth, which could sterilize planetary surfaces and strip away atmospheric components needed for life. However, red dwarfs also burn for trillions of years, providing stable energy sources that could support biological evolution over vastly longer timescales than sun-like stars allow. The tidal locking of K218b creates extreme temperature gradients between its day and night sides, but atmospheric circulation might moderate these extremes sufficiently to maintain habitable conditions. Some models suggest that tidally locked planets might have stable temperate regions along the terminator line where day meets night, potentially providing havens for life even under otherwise extreme conditions. The high atmospheric pressure inferred for K2-18b might actually enhance its habitability in some ways. Higher pressures increase the boiling point of water, allowing liquid water to exist at higher temperatures. This could expand the range of potentially habitable conditions and provide protection against the vacuum of space for any surface life that might exist. The search for life on K2-18b and similar worlds requires developing new observational strategies and theoretical frameworks. Traditional biosignature searches have focused on gases like oxygen, methane, and water vapor that are associated with Earth-like biology. Expanding this search to include gases like dimethyl sulfide and other potential biosignatures could reveal forms of life that operate through different biochemical pathways. The implications for SETI, the search for extraterrestrial intelligence, are equally profound. If life is common on super-Earths around red dwarf stars, and if such life can evolve intelligence over the vast timescales available around these long-lived stars, then technological civilizations might be far more numerous than previously estimated. The longevity of red dwarf stars means that any civilizations that develop around them might have billions of years longer than human civilization to advance their technology. The detection also highlights the importance of atmospheric diversity in assessing planetary habitability, rather than searching only for atmospheric compositions similar to Earth's. Astrobiologists must consider a much wider range of possible atmospheric chemistries that might support life. This expanded perspective requires developing new theoretical models and observational techniques capable of detecting and interpreting non-Earth-like atmospheric signatures. The societal implications of potentially detecting life on K2-18b extend far beyond the scientific community. Confirmation of life on an exoplanet would represent one of the most significant discoveries in human history, fundamentally altering our understanding of our place in the universe and our relationship with the cosmos. Such a discovery would likely have profound effects on philosophy, religion, and human culture more broadly. The technological achievements that enabled this discovery demonstrate the rapid progress in astronomical capabilities and suggest that even more detailed studies of exoplanet atmospheres will be possible in the near future. Next-generation telescopes and instruments will enable the search for biosignatures on smaller, more Earth-like planets and provide the sensitivity needed to detect weaker atmospheric signals. International collaboration has been crucial to these discoveries, involving researchers from around the world working together to design missions, analyze data, and interpret results. The global nature of this scientific endeavor reflects the universal human interest in understanding our place in the universe and searching for life beyond Earth. The ethical considerations surrounding the potential discovery of life on exoplanets are only beginning to be explored. Questions about how such discoveries should be announced, how to avoid contamination of potentially life-bearing worlds, and how to conduct responsible searches for extraterrestrial intelligence require careful thought and international coordination. The discovery also emphasizes the importance of continued investment in fundamental scientific research and space exploration. The technologies and techniques that enabled the detection of atmospheric components on K2-18b resulted from decades of research and development in astronomy, engineering, and related fields. Maintaining and expanding these capabilities will be essential for answering the fundamental questions about life in the universe that this discovery has raised. Red dwarf stars, the most numerous stellar inhabitants of our galaxy, present a fundamentally different environment for planetary formation and evolution compared to sun-like stars. Understanding these differences proves crucial for interpreting the significance of K2-18b's atmospheric composition and assessing the potential for life around the most common type of star in the universe. Red dwarfs, formerly classified as M-dwarf stars, comprise roughly 75% of all stars in the Milky Way galaxy. These stellar remnants burn hydrogen fuel so slowly that they can maintain nuclear fusion for trillions of years, far longer than the current age of the universe. The smallest red dwarfs will continue shining long after massive stars have exhausted their fuel and died, making them potential hosts for life over timescales that dwarf the entire history of the cosmos. Today, the physical characteristics of red dwarf stars create unique conditions for any orbiting planets. With masses ranging from about 8 to 60% of our Sun's mass, red dwarfs burn at much lower temperatures, typically between 2,500 and 4,000 degrees Kelvin compared to the Sun's 5,778 degrees. This lower temperature shifts their energy output toward longer wavelengths, producing primarily infrared radiation rather than the visible light that dominates our Sun's spectrum. The reduced luminosity of red dwarf stars means that planets must orbit much closer to maintain temperatures suitable for liquid water. K2-18b orbits its star at a distance of only 0.1 for astronomical units, roughly 1/7 the distance between Earth and the Sun. At this proximity, most planets become tidally locked to their stars, with one hemisphere permanently facing the star while the other remains in eternal darkness. Tidal locking creates extreme environmental conditions that have no analog on Earth. The day side of a tidally locked planet receives continuous stellar radiation, potentially reaching temperatures hot enough to vaporize rock, while the night side experiences perpetual cold that could freeze atmospheric gases solid. However, atmospheric circulation might moderate these extremes, redistributing heat and creating more temperate conditions across the planet's surface. The magnetic activity of red dwarf stars presents both challenges and opportunities for planetary habitability. Young red dwarfs are notoriously active, producing powerful stellar flares that can increase their brightness by orders of magnitude within minutes. These flares release intense bursts of ultraviolet and X-ray radiation that could sterilize planetary surfaces and strip away atmospheric components essential for life. However, red dwarf activity decreases significantly with age. While young red dwarfs might be hostile to life, older systems like K2-18, which is estimated to be several billion years old, provide much more stable environments. The reduced flare activity in mature red dwarf systems might allow planets to maintain substantial atmospheres and potentially support biological processes. The ultraviolet radiation environment around red dwarf stars differs significantly from that around Sun-like stars. While red dwarfs produce less total ultraviolet radiation than more massive stars, they can produce intense ultraviolet flares that briefly exceed the output of much larger stars. This variable ultraviolet environment creates unique photochemical conditions in planetary atmospheres that could affect the formation and destruction of various atmospheric components. The spectral characteristics of red dwarf stars have important implications for photosynthesis and potential biological processes on orbiting planets. Red dwarfs emit most of their energy in the near-infrared portion of the spectrum, wavelengths that terrestrial plants cannot efficiently use for photosynthesis. However, life around red dwarfs might evolve different photosynthetic mechanisms optimized for them. Available stellar radiation. Atmospheric heating patterns on planets around red dwarf stars create circulation systems unlike those on Earth. The permanent day-night temperature gradient drives powerful atmospheric flows that transport heat from the day side to the night side. These circulation patterns could maintain global temperatures within ranges suitable for liquid water, even under the extreme radiation conditions created by tidal locking. The formation and evolution of planetary systems around red dwarf stars might follow different pathways compared to systems around more massive stars. The lower mass and cooler temperatures of red dwarf protoplanetary disks could affect the condensation and migration of planetary building materials, potentially leading to different planet populations and characteristics. Water delivery to planets in red dwarf systems represents a critical factor in their potential habitability. The close inhabitable zones around red dwarfs mean that planets might form in regions too hot for water ice to condense initially. Water delivery through asteroid and comet impacts might be necessary to establish the water inventories needed for habitability. But the dynamics of such delivery processes around red dwarfs remain poorly understood. The atmospheric retention properties of planets around red dwarf stars depend on complex interactions between stellar radiation, planetary magnetic fields, and atmospheric composition. High-energy radiation from active red dwarfs can drive atmospheric escape through several mechanisms, potentially stripping away the atmospheres of planets that lack adequate magnetic protection. However, planets with sufficient mass and magnetic field strength might retain substantial atmospheres despite the challenging stellar environment. K218b's apparent ability to maintain a complex atmospheric composition suggests that atmospheric retention is possible around red dwarf stars, at least under certain conditions. The search for life around red dwarf stars requires expanding traditional concepts of habitability to account for the unique conditions in these systems. The conventional definition of the habitable zone, based on the potential for liquid water on planetary surfaces, might need modification to account for different atmospheric compositions and circulation patterns. Around red dwarfs, subsurface habitability represents another important consideration for planets around red dwarf stars, even if surface conditions are too extreme for life. Subsurface environments might provide stable refuges where biological processes could occur. Tidal heating from orbital interactions could maintain subsurface liquid water even on planets outside the traditional habitable zone. The long lifespans of red dwarf stars provide unprecedented opportunities for biological evolution and development. While sun-like stars burn for roughly 10 billion years, red dwarfs can maintain stable nuclear fusion for hundreds of billions or even trillions of years. This extended timeline could allow for evolutionary processes and technological development over scales that are difficult to comprehend from a human perspective. The prevalence of red dwarf stars in our galaxy means that a significant fraction of potentially habitable planets likely orbit these stellar remnants. Recent surveys suggest that most red dwarfs host planetary systems, and many of these systems contain planets in the habitable zone. If even a small fraction of these planets can support life, the total number of inhabited worlds in our galaxy could be enormous. The detection of atmospheric oxygen on K218b represents the first detailed atmospheric characterization of a potentially habitable planet around a red dwarf star. This discovery provides crucial observational constraints on theoretical models of red dwarf habitability and suggests that detailed atmospheric studies of similar systems might reveal additional potentially habitable worlds. Future observations of red dwarf planetary systems will benefit from the infrared capabilities of the James Webb Space Telescope and other advanced instruments. The infrared emission from red dwarfs matches well with Webb's spectral coverage, enabling detailed studies of planetary atmospheres that would be much more difficult around hotter, more massive stars. The study of red dwarf habitability also has important implications for the search for extraterrestrial intelligence. If technological civilizations can develop around red dwarf stars, their potential longevity could far exceed that of civilizations around shorter-lived stars. Ancient civilizations that have had billions of years to develop their technology might exist around the oldest red dwarf systems in our galaxy. The future of exoplanet. The detection of oxygen in K218b's atmosphere represents just the beginning of a revolutionary era in exoplanet science, where detailed atmospheric characterization of potentially habitable worlds becomes routine rather than exceptional. The techniques and technologies that made this discovery possible are rapidly advancing, promising even more sophisticated observations of alien atmospheres in the coming decades. The James Webb Space Telescope, despite its groundbreaking capabilities, represents only the current state of astronomical technology. Next-generation space telescopes already under development will push the boundaries of atmospheric detection even further, enabling studies of smaller, more Earth-like planets around a broader range of stellar types. These future missions will transform our understanding of planetary atmospheres and their potential for supporting life. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct a comprehensive survey of exoplanets using gravitational microlensing techniques. While not primarily designed for atmospheric studies, Roman will discover thousands of new exoplanets, including many in Earth-like orbits around Sun-like stars. These discoveries will provide targets for detailed atmospheric follow-up observations by other telescopes. Ground-based astronomy is also experiencing a revolution that will complement space-based observations. The next generation of extremely large telescopes, including the 30-meter telescope, the Giant Magellan Telescope, and the Extremely Large Telescope, will have primary mirrors exceeding 25 meters in diameter. These massive instruments will provide unprecedented resolution and sensitivity for exoplanet observations. particularly when combined with advanced adaptive optics systems that correct for atmospheric turbulence. Direct imaging of exoplanets represents the ultimate goal for atmospheric studies, allowing astronomers to observe the light from planets without the complications introduced by stellar contamination. Current direct imaging techniques are limited to very massive planets orbiting far from bright stars. But future space-based coronagraphs will enable direct observations of potentially habitable planets on nearby stars. The proposed HabEx and LoveWar mission concepts, currently under study by NASA, would employ sophisticated starshade or coronagraph technologies to block the overwhelming light from host stars while serving the much fainter light from orbiting planets. These missions could directly measure the atmospheric composition, surface properties, and even potential biosignatures of dozens of potentially habitable exoplanets. Technological advances in detector sensitivity and stability will enable the detection of increasingly subtle atmospheric signals. New detector technologies based on superconducting materials can achieve theoretical limits of sensitivity, detecting individual photons with unprecedented precision. These detectors, when combined with advanced data analysis techniques, will enable atmospheric studies of planets that are currently beyond observational reach. Machine learning and artificial intelligence are revolutionizing the analysis of astronomical data, including exoplanet atmospheric observations. Advanced algorithms can identify patterns in spectroscopic data that might escape human analysis, potentially revealing atmospheric components or properties that traditional analysis techniques would miss. These computational approaches are particularly valuable for analyzing the massive datasets that future surveys will generate. The development of new observational techniques continues to expand the toolkit available for atmospheric studies. Transit timing variations can reveal the gravitational effects of additional planets in a system, providing context for understanding atmospheric evolution. Phase curve observations track how planetary thermal emission changes as planets orbit their stars, revealing information about atmospheric circulation and heat redistribution. Atmospheric escape studies represent another frontier in exoplanet science, helping astronomers understand how planets lose atmospheric components over time. Observations of hydrogen escaping from exoplanet atmospheres provide insights into atmospheric evolution and the long-term stability of potentially habitable conditions. Future missions will extend these studies to track the escape of heavier atmospheric components like oxygen and water vapor. The search for biosignatures is expanding beyond traditional gases like oxygen and methane to include a broader range of potential biological indicators. Gases like phosphine, dimethyl sulfide, and various organic compounds could serve as biosignatures under different environmental conditions, developing the observational and theoretical frameworks needed to detect and interpret these alternative biosignatures requires ongoing research and technological development. Seasonal and temporal variations in exoplanet atmospheres offer additional windows into atmospheric processes and potential biological activity. Long-term monitoring campaigns using multiple telescopes could reveal changes in atmospheric composition related to weather patterns, seasonal cycles, or even biological metabolism. Detecting such variations requires observational stability and precision that pushes current capabilities to their limits. The study of planetary system architecture provides crucial context for understanding individual planet atmospheres. Planets do not evolve in isolation but are affected by gravitational interactions with other planets, stellar evolution, and the long-term dynamics of their host systems. Understanding these broader contexts helps interpret atmospheric observations and assess long-term habitability prospects. Laboratory astrophysics research plays an increasingly important role in supporting exoplanet atmospheric studies. Precise measurements of molecular absorption properties under various temperature and pressure conditions provide the fundamental data needed to interpret astronomical observations. High pressure, high temperature experiments help understand atmospheric chemistry under conditions that don't exist on Earth but might be common on exoplanets. Theoretical atmospheric modeling continues to advance, incorporating increasingly sophisticated treatments of atmospheric chemistry, dynamics, and radiative transfer. Three-dimensional climate models can simulate the complex atmospheric circulation patterns on tidally locked planets, providing predictions for observable atmospheric properties. These models help guide observational strategies and interpret complex atmospheric data. The integration of multiple observational techniques will provide more complete pictures of exoplanet atmospheres than any single method can achieve, combining transmission spectroscopy, emission spectroscopy, and direct imaging observations of the same planet can reveal different aspects of atmospheric structure and composition. This multi-technique approach helps resolve ambiguities and provides more robust atmospheric characterization. International collaboration will remain essential for advancing exoplanet atmospheric studies. The complexity and cost of next-generation space missions require partnerships between multiple space agencies and research institutions, coordinated observational campaigns using multiple ground-based and space-based telescopes can achieve scientific goals that no single facility could accomplish alone. The development of standardized data analysis and archival procedures will facilitate the comparison and combination of observations from different telescopes and missions, common data formats, analysis tools, and quality metrics enable the astronomical community to make the most effective use of expensive observational resources and build upon previous discoveries. Public engagement and education play crucial roles in supporting the continued development of exoplanet science. The search for life in the universe captures public imagination and helps build support for the long-term investments in basic research that make these discoveries possible. Effective communication of scientific results and their implications helps maintain public interest in astronomy and space exploration. The potential discovery of life on exoplanets raises important questions about planetary protection and the ethics of interstellar exploration. Developing protocols for responsible exploration of potentially life-bearing worlds requires careful consideration of how to avoid contamination while enabling scientific investigation. These discussions are becoming increasingly relevant as our ability to study exoplanets in detail continues to improve. The search for atmospheric biosignatures also requires careful consideration of false positive signals that might mimic biological activity. Abiotic processes can produce some gases that are considered potential biosignatures, making it essential to develop robust criteria for distinguishing biological from non-biological atmospheric signatures. This challenge requires ongoing research into atmospheric chemistry under a wide range of environmental conditions. The ultimate goal of exoplanet atmospheric studies is to determine whether life exists beyond Earth and to understand the conditions that enable biological processes to emerge and thrive. K218b represents a crucial step toward this goal, demonstrating that detailed atmospheric characterization of potentially habitable exoplanets is achievable with current technology. The rapid pace of technological development suggests that definitive answers to questions about extraterrestrial life may be within reach in the coming decades.